In this video, we'll get a quick introduction to sampling distributions, the key to turning data into information or inferences about a broader population. Consider the big picture. In any data analysis, we're typically interested in learning about some broader population of interest, but for various reasons, we only have access to data on a sample from this population. For example, suppose we wanted to learn about the average weight of a tuna fish. Now, not only is this population always in flux, there's no possibility of weighing every tuna fish in the world. Nor would we want to, even if we could. It would disrupt the entire ecosystem. Instead, what we can do is select and weigh a sample of tuna. Similarly, to learn about the safety of a car, we can select and run a sample of cars through a crash test procedure, but not all cars, because then there wouldn't be any cars. Or to study sleep habits among college students, we can select and survey a sample of students. We don't have to, nor could we, enroll all students in a sleep study. So settling for sample data is simply a reality. And in working with sample data, there are a few things to keep in mind. Data on a mere sample can provide mere estimates of the trends in the broader population. Further, different samples of different data can produce different estimates, some accurate, some not. And unfortunately, since all we have in reality is our sample and we don't know the actual trends in the population, we can't know for certain whether our estimate is one of the accurate ones. Now this seems pretty bleak, but this is where sampling distributions come in. Sampling distributions help us understand the degree to which our estimates might vary from sample to sample. Hence, help us understand the potential error in our sample estimate. In the coming days, you'll learn the fundamental properties of a sampling distribution. But before you do, it's important to understand what exactly a sampling distribution is. To this end, suppose we're interested in the relationship between two arbitrary variables, y and x, among the entire max student population. If we were able to actually gather data on all 2,000 plus students, we'd be able to see a picture like that here, where the population model trend is described by y equals beta 0 plus beta 1x. But suppose this is all hypothetical, and that we can't actually get data for all students. Instead, in reality, suppose that we have to settle for data on a sample of 20 max students. Though this sample can't be perfect, it does provide an estimate of the population model trend. We denote this estimate by y equals beta hat 0 plus beta hat 1 times x. In general, in the modeling world, whenever you see a hat or a caret on top of a letter, it represents an estimate. For example, beta hat 1 is an estimate of beta 1. But hypothetically, we could have gotten a different sample. So this is our sample, but it could have been different. And this sample would produce a slightly different estimate. Or hypothetically, we could have gotten yet a different sample of 20 students, or another, or another, or another, or another. I'm not going to keep going because in total there are more than 3.9 times 10 to the 47 different possible samples of 20 students that I could take from the broader population of 2,000 plus students. If you're familiar with counting or combinatorics, I calculated this using 2,000 choose 20. Now, each of these 3.9 times 10 to the 47 different possible samples might provide a slightly different estimate of the model trend. I've selected just a small subset of those possible model trends here. Now, since we can get different model trends based on what sample data we happen to get, each sample estimate of the trend might have a slightly different estimate of features such as the slope, beta hat 1. That is, these sample slopes, beta hat 1, can vary from sample to sample. The collection of the different possible sample slopes, that is, the collection of the slopes in these lines, are shown here. They range from, say, roughly a slope of 1 to roughly a slope of 3. In fact, this collection is what we refer to as the sampling distribution of the sample slopes beta hat 1. In conclusion, we're typically interested in the trends among some population, yet can only estimate the trends using data from a sample. The sampling distribution of one of our sample estimates beta hat is a collection of all possible estimates that we could observe based on all possible samples of the same size n from the population. Thus, a sampling distribution captures the degree to which our estimate could vary from sample to sample. This idea is expressed in picture form here. From the population, we could get different possible samples, each sample potentially producing a different estimate, beta hat. And the collection of these possible estimates is the sampling distribution. Before concluding, keep in mind that everything we've talked about here is hypothetical. In reality, we take one sample from the population. We don't actually go out and take thousands and thousands and thousands and thousands of different samples. And we don't have to. Though it's a hypothetical idea, we'll learn that sampling distributions share some common properties that can help us understand the potential error in our one sample, thus what we can or cannot use our data to say or conclude about the broader population.